Hey everyone, Mr. Fransky here. I'm going to take a look at type 1 and type 2 error in a binomial problem here. And we could also do this with a Poisson. The process is very similar. But this problem happens to be binomial. And again, they don't mention it's binomial, but let's take a look at what's going on. At a local school, it is believed that during recess, 75% of the students will use the slide on the playground. Okay, so 3/4 of the kids will use the slide. School administration believes that if the teacher on recess duty goes down the slide, the percent of students using the slide will increase. All right, so Mr. Fransky's on recess duty. He uses the slide, and now all the kids want to use the slide, obviously. So over the course of recess, with a teacher using the slide, they look at 230 kids, and the hypothesis is tested at a level of 5% significance. Okay, so again, they don't say it's binomial, but let's look at what they tell us. 230 students are observed. That's a cap, right? So we can't have infinite students, right? That's an n, so n is 230. And they also give us a probability, right? This is our, in binomial distributions, we call this p. We have to be a little bit careful because p-value now that we have significance testing, we have to be a little bit careful about that. But this is what is believed to be true. Okay, so they're saying it's a binomial distribution with 230 kids and a probability of success of 0.75. Sorry, I snuck that in there. So let's see what we do. Null and alternative hypothesis. So the null hypothesis is that there hasn't been any change, right? The probability, the proportion is 0.75. That is the percent of kids that use the slide. The alternative is that if the teacher uses the slide, p is now greater than 0.75. So they want us to find the probability a type 1 error happens. Remember, that's just the probability that we're in the tail when we reject the null hypothesis, but maybe we shouldn't have. So we reject, but we shouldn't. So that means that the p is correct, the 0.75, but we just happen to be in the tail. And that's usually, with a normal test, that's just equal to alpha, right? The whole idea with a normal test is that you cut off the value that gives you 5% in the tail, and that's exactly the probability that you would find an example that far or further away. But because we have a binomial distribution, we have this idea that we have discrete values, right? So there's going to be some value where we chop it off, and to the right is going to be less than 0.05, and to the left is going to be greater than 0.95. So two ways we can do it. We can do it from the right or from the left, and we're going to take a look at each way. But we have to figure out what is that value, right? What is the critical region, and how small is that percent? It's not going to be exactly 5%. We have to figure that out. So first of all, I want to see how many kids do I expect to use the slide? Well, I have 230 kids, and I expect 75% of them to use the slide. I'm just multiply by 0.75. So 75% of 230, I expect 172. So to reject this, I'm going to expect we have to be bigger than that. Maybe 180 or 190, something like that might be in our rejection zone. But let's drop it into our table and find out. So I'm going to do just, first one I'm going to do just on the left side, because binomial CDF will give us 0 up until x, right? We want to figure out what that x value is. And we'll see what it ends up being. So I'm going to do distribution. I'm going to go to binom CDF, and I have 230 kids. There's a 0.75 chance that they use the slide, and I'm just going to drop x in there because I want to see what it is up to 170, 180, whatever that value is going to be. So I'm going to go to my table set, and we might want to start this somewhere around what we expect, right? So I might start at around 170. We expect 172, so around 170, that's when I'll start kind of getting into actual values. So if I go to my table, and we see here that, oops, back to my table. So we see, yeah, we're getting pretty close to half, right? So there's about a 50% chance that up to 173 kids use it, and it's going up, up, up. We're looking for the first value that's bigger than 95%, and there it is. Right? So 183 is the first value that's bigger than 95%. So what that tells me, if I use red here, this value right here is 183. That is the first time that I have gotten over 95% on the left side of what like kind of my cutoff line is. So that means this value is 184. So this means that we would reject the null hypothesis if we get 184 or more kids using the slide. So greater than or equal to 184. And we can see like the probability there, if we subtracted from 1, we could figure out what that value is. But I'm going to use the 1 minus binomial CDF to get the exact value. So we could do that. We could just subtract that 0.955 from 1. But what I'm going to do is in my y equals, I'm going to do a second one. And you could just do this from the get-go. But I'm going to do 1 minus, go to my distributions, binom CDF, 230 kids. Probability is 0.75, and we're just dropping x again. Close the parentheses. And if I go back to my table, we should still be at the same spot. And we can see here, so when I hit that value, the kind of shortcut here is the first value under 5%. The first value under 5% is that 0.04447, right? So that's kind of the shortcut, is that the probability of a type 1 error happening, we want it to be under 5%, and the first time that we get under 5 is, so probability of type 1 error is 0.04447, or about 0.0445, right? So again, before, we want alpha to be 0.05, but the actual alpha value is 0.0445. We can't do a bigger value. We can't use that 0.0615. We have to use the first value that's under. And sometimes it'll be quite a bit under, right? It could be like 3 or 2%. That might be the first time that you get under the alpha value that you want, right? Now, let's also think about this number here, because the 183 can be a little misleading. I see a lot of people think the critical region starts at 183. But let's think about what this means, right? So that 183 for y2, what we're saying there is it's 1 minus binom CDF at x equals 183. Well, 1 minus binom CDF at 183, where is that actually going to start? That takes away everything 183 and less, so it starts at 184 and more. So the two ways we did it agree, right? We did binom CDF up to 183, and that gave us this value at 0.095. And then the 1 minus 183, that both of those confirm that we need 184 or more in order to reject the null hypothesis. Sample determined that 185 students used the slide. So what would be the conclusion to this test? Well, 185 is indeed in my critical region. So 185 is greater than or equal to 184. Therefore, we reject the null hypothesis and claim sufficient evidence that more than 75% of students use the slide. Now, if we want the p-value we can get by looking at our calculator again here. So if we want to know the probability that 185 or more, right? So we want 185 or more. That's going to be 1 minus binomial CDF at 184. Right? Because we want to take away everything 184 or less, so it's going to be 185 or more. So on my calculator, if I go to the 184 value, I'm sorry, I keep doing that, that gives me a probability of 0.0316, right? And we could have used that as well. We used the critical region before, but P is less than 0.05. Therefore, we reject the null hypothesis and claim sufficient evidence that more than 75% of students use the slide. So now we get into some type 2 error. Remember, type 2 error means that we do not reject, but we should have. Okay? And so they'll always tell you an actual answer, right? So before the sample was taken, the school secretary claimed the true probability was 81%, right? So we're operating with the wrong information, right? We're dealing with a 0.75, but it actually should be 81%. And so if we do not reject, well, we can look at our critical region to see what that means. So do not reject, that means that we must have had 183 or fewer students use the slide, because we were operating off of this 0.75 idea. That created our critical region. We found that if we have 184 or more, we'll reject the null hypothesis. So if we do not reject, that means we must have had 183 or fewer. Now, what's the probability that that happens with a correct proportion of 81%? So we want to know what is the probability that the number of kids that use the slide is less than or equal to 183 given that the actual proportion of kids that use it is 0.81. So that's just a binomial CDF. I'm going to use binom CDF. I'm going to do it with 230 kids. The probability is 0.81 now. And just like when we were doing normal distributions, right, you have to change where the actual metric is that you're using. And we're going to do up to 183. And that'll give us the probability that we don't reject the null hypothesis, but we should have. I'm going to do that in a regular calculator window. So I'm going to do distribution, binom CDF. We have 230 kids. We are now assuming the secretary is right. There's 0.81 is the actual probability a student uses a slide. But we have not rejected the null hypothesis, so we only could have had up to 183 kids using it. And that gives us a probability of 0.3142-ish. And that's the probability of a type 2 error, so about 31.4%. That we commit a type 2 error. We did not reject the null hypothesis, but we should have. So this is all about defining that critical region, finding that value where you have less than 5% in the tail, and you have more than 95% in the do not reject region. All right? Hopefully this is helpful.